So we are talking about adiabatic mixing of air streams, and here there are, as it is shown in the schematic diagram, there are two ducts. One duct is carrying air at certain condition, let's say state 1. Another duct is carrying air at another state, at state 2, let's say. The flow rate, mass flow rate of the dry air here in this duct stream 1, you can call it, is m dot da1, and it has certain properties like enthalpy and humidity ratio, temperature, dry bulb temperature, wet bulb temperature, etc. And you are showing that with the help of suffix 1. Now the mass flow rate of stream 2 is m dot da2, and it has its own state of parameters or properties, and it is flowing through this duct. Now both these streams are getting mixed, and obviously they will produce some other state, and the mass flow rate would be m dot da3. Now this is there is no loss of mass. Okay, so obviously there is mass conservation. You can write the equation for that, and then the boundaries are also perfectly insulated. So it's an adiabatic mixing process. Adiabatic mixing process. So you can also apply the mass balance as well as moisture balance, mass balance of dry air, moisture balance of water vapor, as well as the energy balance. And with the help of that, you can get the value of various properties or parameters at after mixing, right? So that is what would be the exercise in this psychrometric process, right? Now we'll talk about these equations, etc. But why should one learn about this process, right? So this process is also very common in air conditioning. Where is this happening? You can see this diagram. What you see here is there is conditioned space here, right? On at the top you can consider the conditioned space. So uh, it's not at the top from point of view of elevation, right? It is this in the, I'm just talking from point of view of this photograph. So on this side there is uh, the conditioned space, air conditioned space. So which you are keeping, where you are keeping the air at lower enthalpy, if it is summer air conditioning case, right? And if it is winter air conditioning case, it could be at a lower enthalpy, right? Because outside conditions the air is at if it is winter air conditioning case, it is higher enthalpy, and because ambient is at much lower enthalpy temperature, and even the humidity may be very less outside if it is winter. Okay, so this is conditioned space, and this return air is taken from this opening here. You know a bit about this from the experiment done on air conditioning system in the lab, right? So where you had two ducts, one is the delivery duct and the other one is the supply duct, right? Okay, so the return, or rather it is return air duct and supply air duct. So return, this is return air duct, and this return air is taken from here, and so that it has a particular conditions. You can say that this is at state 1, right? This is at state 1. Now here if you're talking about, let's say, a split AC, there is no provision for the outside air to come in and get mixed with the return air. What happens is the room air is taken and it is its enthalpy is reduced and it is delivered back into the room. But if you're talking about somewhat larger systems or even central air conditioning systems, there is provision for outside air to be taken before it is processed in the air conditioning unit or air handling unit. So here, as you can see, there is a provision for to take the outside air, and there is a damper here with which you can control the amount of outside air that you want to take. As you will realize that this outside air actually, if you're talking about summer air conditioning, the enthalpy would be very high. And here you have already decreased the enthalpy and you are taking that air. When you mix it with this, you are going to increase the enthalpy, and that will create an additional load on your air conditioning unit or air handling unit here, air conditioning unit here. So uh, you should not unnecessarily add more amount of outside air, but of course you should add enough amount so that the amount of pollutant inside the room remain in check, do not cross the recommended limits. And that's that. For that, required oxygen level should be maintained, required CO2 level should be limited. And to do that, you have to add, you have to take the outside air and you have to mix it with this, with the return air stream. So you are doing this, mixing them, and then it is processed further. So here this is nothing but, you can call it adiabatic mixing. So there is one airstream with certain properties of air or state of air, another airstream with a different state. You mix them, you create third state, right? So you want to know what is this state, what are the properties of air, and what are the other parameters after you mix them, because then you are process it in the air conditioning unit. So only if you know the inlet to this air conditioning unit and some outlet is prescribed, you can calculate certain parameters for this air conditioning unit. So right now our focus is on this mixing process. So I've already explained the things with the help of this schematic diagram. And now we are talking about the energy balance and mass balance. So this middle equation is nothing but the mass balance of dry air. So m dot dA1 plus m dot dA2 is equal to m dot dA3, right? So that's nothing but the mass balance. This stream plus this stream, and there is no loss of mass here. So this is m dot dA3. And then the equation, another equation here is m dot dA1. This is moisture balance, W1 plus m dot dA2 W2 is equal to m dot dA3 W3. So this is moisture balance. Okay, how is it moisture balance? Okay, so how is it moisture balance? You are this is humidity ratio, right? This is humidity ratio, and you multiply it with the mass flow rate of dry air. When you do that, what you get is kilogram of water per second, right? That will be the unit here. So basically, this is nothing but the moisture balance. So the rate at which you are getting moisture from the stream 1 and the rate at which you are getting the moisture from stream 2, there is no moisture loss. So the stream 3 will have this much amount of moisture, right? That is the moisture balance equation. And the first one is the energy balance equation, right? Or enthalpy balance equation. So you are getting some enthalpy. You can say this is the rate at which the enthalpy is entering stream 1 through stream 1, the rate at which the enthalpy is entering through stream 2, and then that is equal to the enthalpy in the stream 3, a rate at which the enthalpy is coming out from section 3, because there is no addition or removal of heat in the system. It's an adiabatic system. When we talk about other case like cooling and dehumidification, at that point you will see that it's not adiabatic. You are taking out heat from the system in that case. So there will be a separate term for that in that case, right? So this is the moisture balance. Okay, and regarding the application, as I explained you earlier, what happens? This is conditioned space. Now the conditioned space may be occupied by people. When people are there, when we exhale, we discharge carbon dioxide in the space. So if there are many people, then the carbon dioxide level will go up. And it's actually not only carbon dioxide, but there are other pollutants also coming out, and we are becoming more and more conscious about this under this pandemic situation. So there could be other pollutants or bacteria, virus, etc. Now, so that should be diluted. If you don't bring the outside air, then the level of the pollutants inside the room will go on increasing. So what you have to do is you have to take outside air, and which has less pollution, as well as the oxygen required oxygen level is there. So with the help of that, you so you mix, when you mix them, you are reducing the amount of the pollutants, and you are then discharging it again or delivering it into the conditioned space, and that's how you keep the CO2 level as well as other pollutant level in control with the help of this. So if you don't bring the outside air, like in case of split AC, what you presume is that you are going to have like loosely built buildings, so there are gaps through which the outside air is coming, or you are opening and closing the door frequently, so from that also the air is outside air is coming, right? So it's generally not advisable to like without any outside air to remain inside a conditioned space, because there could be pollution generation inside the space. And this is just one type of pollution generation I am saying. There could be other ways in which the pollutants could be generated. Of course, here the assumption is that the outside air is not having very high pollution levels, right? So only in that case you can call it fresh air, and you can keep the pollutant level in check. Okay, so let's take an example on adiabatic mixing, because we are interested to know the state after mixing. So you can read this example. A stream of 2 meter cube per second of outdoor air at 4 degrees Celsius dry bulb temperature and 2 degrees Celsius thermodynamic wet bulb temperature is adiabatically mixed with 6.25 meter cube per second of recirculated air at 25 degrees Celsius dry bulb temperature and 50% RH. Find the dry bulb temperature and thermodynamic wet bulb temperature of resulting mixture. Right. So here there are two states. One is 4 degrees Celsius dry bulb temperature, 2 degrees Celsius wet bulb temperature. Actually, this could be a winter air conditioning case. So outdoor air is at a very low temperature, 4 degrees Celsius and 2 degrees Celsius, right? So you first locate that point. If you are doing showing the process on psychrometric chart, as I have been telling, that charts are good for visualization of the processes, though for calculations you might use the formula and tables, which can be more accurate, but still plotting them on psychrometric chart also helps you to get the visualization of the processes. So point one is the it should be located, and again point two also should be located on the psychrometric chart. So point two is 25-degree dry bulb temperature and 50% RH, and this two could be the room conditions, and you are taking the return air from room, you are recirculating that air, but before that you are mixing the outside air with that. So you are interested to know what will be the state after mixing. So that's the objective of this example. So let's look at point 1 and 2 on the psychrometric chart. So one of them, the point 1 is 4-degree dry bulb and 2-degree wet bulb. Okay, so let's take one point there. So 4 degree, 1, 2, 3, 4, degree dry bulb temperature and 2 degree wet bulb, right? So could be somewhere here. This is 5, this dashed line. This dashed line is for 5, this one is for 4, this is for 3, this is for just a minute, sorry. This dashed line is for 5, this is 4, 3, and this one is for 2, right? So this line is for 2. This dashed line is for 2. So 4 and 2. So the point should be somewhere here. 5, 4, 3, and 2, right? So this is your point 1, right? This is your point 1. So look at that point on the psychrometric chart. This is point 1. 4 degrees Celsius dry bulb temperature and 2 degrees Celsius wet bulb temperature, right? Okay. Now look at point 2. It is 25 degrees Celsius dry bulb temperature. So let's put this there. 25 degrees Celsius dry bulb temperature and 50% RH. So this is 25 and 50% RH is here. Relative humidity is here. So this is the second point, right? This is the second point. Okay, so that is stream 2, the condition of stream 2, which is coming from the conditioned space, right? And the other one is the outdoor air condition. So this is stream 2, right? The conditioned space. Now these two are getting mixed. Of course, the flow rates are not the same. Now it is seen that after you mix them, the state that is produced is somewhere on the straight line joining these 2 points. Okay, somewhere on the straight line joining these 2 points, right? That is what is observed. So your point 3 will be somewhere on the line joining 1 and 2. Line joining, if you want to solve it graphically, even that is possible, right? You have to take the ratio of the mass flow rates, and with the help of that you will be able to get the proportion where the point 3 will be. Obviously point 3 will be near to the higher mass flow rate. So which one is higher mass flow rate? The in duct 2, the recirculated air will always be higher flow rate most of the times, right? Because if you bring in more outside air, it's going to be your air conditioning system will have higher load. Okay, so normally you will have higher rate of circulation or recirculation as compared to the fresh air flow rate. So this is about like your point 3 will be somewhere on this line, and would all obviously be closer to point 2 because the at state 2 the flow rate is higher. Okay, so now we want to solve this example. It could be solved graphically as well as with the help of formula. So we'll do probably these things simultaneously. So what are the steps to solve this? What you want to get? You want to get the dry bulb temperature at this point. After mixing, what is the dry bulb temperature, right? And the other thing is that what is the like only one parameter is not enough. So you want wet bulb. You in some way you want to show the humidity ratio at this point also, or the amount of humidity. So either you get the either you get the wet bulb temperature or you get the humidity ratio. You also might be interested in enthalpy at point 3 because finally it's the enthalpy. At this enthalpy, it will go into the air conditioning unit, and there you have to reduce the enthalpy of this air. Okay, so the various properties at point 3 could be of interest. So first thing, what you have to do is, even if you want to get it graphically, you have to get the mass flow rates. What is given is not the mass flow rate, it is volume flow rate. So 2 meter cube per second and 6.25 meter cube per second, they are the volume flow rates of the 2 streams. So you have to first get the mass flow rate. To get the mass flow rate, what you can do is, what is the specific volume at point 1 and what is the specific volume at point 2, and you have to divide it with these specific with the like you have to divide the volume flow rate with the specific volume. Of course, you can get the specific volume by reading it from here on the psychrometric chart, right? That is one way of getting the specific volume. If you are not very much concerned about being very accurate, you can do that for quick calculations. The other way is to get the specific volume with the help of a formula. And with the help of the formula, in that formula, you need the humidity ratio also. So you need to get the humidity ratio before you get the specific volume if you want to use the formula. So let's see how you can do that. So these are the given conditions: the dry bulb temperature of stream 1 and the dry bulb temperature and wet bulb temperature of stream 1, then dry bulb temperature of stream 2. The relative humidity is 50%, 0.5. The volume flow rates are given. These are the two volume flow rates, and you want to get the humidity ratio at state 1. So you can use this formula. You can use this formula where T star is the wet bulb temperature, WS star is the humidity ratio at the saturation condition at wet bulb temperature, which you have to get from the psychrometric table, and T is nothing but the dry bulb temperature. So with the help of these parameters, you can get the value of humidity ratio at state 1. So how much is WS star for state 1? Because the wet bulb temperature is 2 degrees Celsius, I can refer to the psychrometric table. For 2 degrees Celsius, you can see 0.004382, that is WS, humidity ratio at saturation. So 0.004382 is W, as it is written here, WS for the state 1, 0.004382. So using this formula, you can get the value of humidity ratio at state 1, and it is 0.00359. Okay, 3.59 grams of water per kg of dry air. So you can understand that it's very dry condition. At state 1, the condition is very dry. You can see it is quite low on the psychrometric chart. So value of humidity ratio is quite low. So outside conditions are cold and dry, right? If you're talking about winter air conditioning. So these are the conditions at state 1. Now, uh, so with the help of W, you can use, you can get the specific volume, right? You can get the specific volume. So this is the specific volume, which is the formula that you are going to use. This is the formula that you are already familiar with this formula. And here T is the dry bulb temperature, P is the total pressure. If nothing is given, you take it 101.325 kilopascal, and with the help of that, you get the specific volume in meter cube per kg of dry air. Now, because I am using the program, there could be some limitations in writing the units, but you are very clear about what is the unit for each, and you should write the unit. You should not miss the unit. So W is kilo. Here it is kilogram of water per kilogram of dry air. Specific volume is meter cube per kg of dry air. Right. So with the help of this formula, you get the specific volume, and you can get the mass flow rate of dry air in stream 1, which is volume flow rate divided by specific volume. So the mass flow rate of dry in stream 1 is 2.532 kg per second. Now you want to get the mass flow rate for stream 2. So for that also, either you read it from the psychrometric chart, right, and get the specific volume and that value. So as you must be, you can, I hope you are able to recall that these are the constant specific volume lines. So it seems to be quite close to 0.86, right? And this is 0.85. So you can say that if you're solving it graphically, it could be somewhere near 0.858 or something, right? So let's also do it with the help of formula and check whether that judgment is good enough or not. So I now So you, for formula, you need to get the value of W2. Now, what are the things given for state 2? Temperature, dryable temperature, and relative humidity. These two things are given. So to get W, you use this formula, 0.62198 62195, and PW upon P minus PW, right? That's the formula that you use, and with the help of that, you get the W2, and then you can get the specific volume. But how do you get the vapor pressure? Vapor pressure at state 2, it is nothing but the saturation pressure multiplied by RH. So how much is the saturation pressure? It depends upon temperature. What is the temperature? It is 25 degrees Celsius. How do you get this saturation pressure? You get it with the help of the saturation properties of water. So saturation properties of water, you want it at 25 degrees Celsius temperature. So at 25 degrees Celsius temperature, the saturation pressure is 3.1697 multiplied by 0.5 will give you the vapor pressure at 0.2. So that is what has been done here, and you get the vapor pressure equal to, water vapor pressure equal to, you may write it in kilopascal. So it is 1.585. That is the water vapor pressure. Okay, so you get the water vapor pressure, and with the help of this formula, you can get the value of W2. So you are familiar with this formula for W, right? So with the help of that formula, you get the, this is the formula 621945, right? PW upon P minus PW, and you get the humidity ratio at 0.2, which is close to 10, right? 10 grams of water per kilogram of dry air. Okay. Now, with the help of the formula, again, this formula for specific volume, you can get the specific volume. So you should get something near 0.858. Yeah, so that judgment was quite good, and it is close to 0.858. Okay, almost the same. So now you can get the mass flow rate in stream 2. So that is volume flow rate divided by specific volume. So that's 0.7282. And after you mix them, what is going to be the mass flow rate? It is m dot dA3, which is equal to sum of m dot dA1 and m dot dA2. So total mass flow rate in stream 3 is 9.814 kilogram per second. Okay. So this is the mass balance, and you want to get the dry bulb temperature. So how can you get the dry bulb temperature? You can use this formula. As I told you, the 0.3 is on the line joining 0.1 and 0.2. So even for temperature, you can write it like this. That is m dot dA3 into T3 is equal to m dot dA1 into T1 plus m dot dA2 into T2, right? So this formula can be used to get the dry bulb temperature at 0.3, because you already know the dry bulb temperature at 0.1, 0.2, m dot dA1, m dot dA2 are known, m dot dA3 is already found. So now you can get the dry bulb temperature at 0.3. So with the help of this formula, you get it 19.6 degree Celsius, right? So you have that temperature now, so you can get the 0.3. How? Okay, so let me just show that point, and then I'll talk how you could have got it graphically also. So 19.6, so somewhere here, 19.6, right? So the intersection of these two, this blue line and orange line, provides you 0.3, right? So 0.3 is here at the intersection, right? So This is how you are able to locate the point 3, and then once you get this point, you can get all other properties of air, right? You can either read it from chart or you can get it from with the help of formula, right? So 19.6 is the dry bulb temperature. Now, how you could have got 0.3 with graphically, right? So as you know, the mass flow rate of stream 2 is higher, and that of 1 was lower. So the total length and length 2 3, that is length 2 3 divided by length 1 2, should be equal to m dot dA1 divided by m dot dA3, right? That should be the ratio. Okay, so that way you can get the 0.3 graphically also, but we did it with the help of formula. And once you have this point, you can read all other things. That is, you can read enthalpy, which seems to be quite close to 40 at 0.3, right? And you can get like you are also interested in the wet bulb temperature at 0.3, so it seems to be quite close to 15, right? It seems to be around 14.5. So that's the wet bulb temperature at 0.3, right? And you can do this exercise with the help of formula also. So that is what has been done here also. So W3, what is the humidity ratio at 0.3? So you can read it from the chart also. You can draw a horizontal line up to the W axis, or you have this formula which can provide you a better estimate. So m dot dA W1 plus m dot dA W2 divided by m dot dA3 would give you the humidity ratio at 0.3, which is 8.26 grams of water per kilogram of dry air. And with the help of the formula for enthalpy, okay, this is the formula for enthalpy. The first part of it shows the sensible heat carried by dry air. The second part provides the heat carried by water vapor. This 2501 is the latent heat at 0 degrees Celsius. 1.86 is the specific heat of water vapor. Water vapor it is, right? It's not liquid water. Water vapor at some average value of temperature, and T is the dry bulb temperature. So with the help of this formula, you can get the enthalpies at various points. At point 1, it was quite low, 13. As it is winter heating case, the outdoor air has very low enthalpy. In summer air conditioning, it is the opposite case. The outdoor air will have very high enthalpy. This is recirculated air, and it has comparatively high enthalpy, winter heating case. But after you mix them, the enthalpy has reduced a bit, right? So what you have to do is you have to again increase the enthalpy and then put it back into the room. So that's what will be done by the air conditioning unit. Okay. And in case of summer air conditioning, it will be the opposite thing. That is, enthalpy H3 will be higher than enthalpy H2. So when you deliver it into the room, you have to reduce the enthalpy of air, and it has to be actually less than the room enthalpy of room air, because the enthalpy is getting added into the room, right? In case of summer air conditioning, the heat from outside is coming, people inside are discharging heat. So in that case, your value of H3 has to be much lower than the value of H2. Okay, but of course the procedure and the equations remain the same. So the wet bulb temperature, as we could see, was around 14.5 degrees Celsius, and that could have been done by trial and error method using the formula also. So the same formula which is used for getting value of W with the help of dry bulb and wet bulb temperature, but here the wet bulb temperature is not known. So what you have to do is you have to get the value of these two, read the value of these two simultaneously from the table and put it in this formula. And if you get this value of W close to W3, then your estimate of wet bulb temperature is good. So you can, of course, it gives you some idea with the help of psychrometric chart. So you can try the values nearby. You can try 14, you can try 15. If you try 16, you will see that the value of W that you get is quite away from this, could be much higher. So you know that it's between 14 and 15. So best estimate you can get is maybe 0.5, and you can take the value of W as average between 14 and 15. This is from the psychrometric tables. So 14 and 15. So 0.010013 and 0.010694. Right. So those are the values of WS. You can take the average of these two and take wet bulb temperature equal to 14.5. When you do that, you find that value of W is quite close to this one. Right. So your 14.5 degrees Celsius could be a good estimate. So this is how you get the wet bulb temperature. Right. So uh, we were interested in getting the state of zero point 0.3, particularly because it gives me the state after mixing, and after this is going to go to the air conditioning unit where you have to either increase or decrease the enthalpy. That's why this mixing case was also an important case. So this was all about the adiabatic mixing of air streams. Now let us discuss the next case, and that is increasing the humidity ratio in the air. And it is shown here what exactly is done. Now, why one would be interested in increasing the humidity ratio, or you can say air humidification? So this could be heating and humidification process, psychrometric process. Heating and humidification, as you might recall, can be carried out in an air washer. If you heat the water which is being sprayed and the air is passing over that, so humidity is also added and the temperature of air is also rising. So one option is to have hot water sprays and pass air over that, and that will increase the temperature and humidity. Another option is to inject steam directly. Now injecting steam directly is more preferable, as you will see with the help of the example which we are going to solve, when you don't want to increase the temperature much but want to increase only humidity. Okay, want to increase the humidity. So in that case, the steam injection would be done. And why this might be needed, this type of process may be done. The reason for that, one of them could be with the winter air conditioning. In winter, the outside the conditions could be very dry. So you want to increase the humidity in the conditioned space, and for that you might inject water vapor or steam into the duct which is carrying the supply air. That is what has been shown here. You may focus mainly upon this part, and this is actually nothing but an RO unit. So you don't want to like here you're vaporizing water and you don't want it to have very high salt content, TDS content. So you are softening that water, and then you're creating sprays of water, and that water evaporates and increases the humidity. So here it is only water which is shown, which is evaporating, but it could be like you soften the water and then you create low pressure, low temperature steam in the boiler, and then you can inject the steam also. Right. So as you can see, this is return air coming from the conditioned space. Again, this could be winter air conditioning. Outside air is mixed, and after that you may want to heat it, and you may also want to inject inject when you inject water, it may vaporize. If you inject in the required amount, it may vaporize completely and increases the humidity, and then that is supplied into the space. There could be industrial applications of this also, when humid atmosphere is needed for a certain process, let's say in textile industries. At that time also you can think of injecting steam into the airstream. So this is about the application. So let's take one numerical, and solve that numerical to understand the various appreciate various parameters in such processes. So the example is moist air at 20 degrees Celsius dry bulb and 8 degrees Celsius thermodynamic wet bulb temperature is to be processed to a final dew point temperature of 13 degrees Celsius by adiabatic injection of saturated steam at 110 degrees Celsius. The rate of dry air flow is 2 kg per second. The final dry bulb temperature of moist air and the rate of steam flows, that is to be found. So condition given, one of the condition is 20 degrees Celsius and 8 degrees Celsius, dry bulb and wet bulbs. That's point 1 here. Okay, you can put it on the psychrometric chart. It is the conditions given are 20 and 8. So 20 degree is the dry bulb temperature and 8 wet bulb. So 8 is here. This is 10. This is 9 and this is 8, right? So 8. So you can see it is quite low on the psychrometric chart. It is quite low on the psychrometric. It means humidity ratio is very low. The outside air is having very low humidity ratio. So you want to increase the humidity ratio by injecting steam. And finally, at what state do you want to supply it? That is what is given, right? The final state of the moist air is given, and that final state should be, only thing given is the dew point temperature, which should be 13 degrees Celsius, right? So where is 13 degrees Celsius? If you read it on this, this is 13 and it intersects the saturation line. So you want to have this much dew point. You want to have this 13. You want to have this much dew point, right? 11, 12 and 13. You want to have this much dew point. Okay, this horizontal line, but you don't know where exactly is this state, right? Where is the final state? It could be anywhere on this line. So you have to locate it, or you have to get the point where it would be, right? On this line where it would be. You have to get one more parameter with the help of which you can locate it, right? So that's what is required. And what is the so dry bulb temperature is to be found as it is asked in this example, right? Dry bulb temperature is to be found, and you are also interested to know what is the rate at which you have to inject the steam, right? Rate at which you have to inject the steam, because like you are using a boiler, so what part of the steam produced there is required in your air conditioning process. So that rate is required. So that can be done with the help of the moisture balance, right? That can be done with the help of moisture balance, right? So you can write the balance equations for this also, right? The balance equation, one of them is quite simple, and that is nothing but the m dot sorry, this is another example. So we are talking about this. Yeah. So whatever is the water vapor here, m dot dA. Now here there is only one stream, and you are just injecting steam into it. So m dot dA into W1 plus m dot W, that is rate at which the steam is injected, is equal to m dot dA W2, right? So because all steam is contained as vapor when you reach state 2, so that would be the balance equation, and similar equation can be written for the enthalpy balance also, because like the steam is injected, but then otherwise the system is well insulated and there are no heat losses from the system. So those equations are used while solving this example also. So at that time you will see the nature of those equations. Yeah. So these are the steps. You will get the humidity ratio at point 1 and 2. With the help of that, you can get the steam injection rate. Then you get the enthalpy of stream 1 as well as enthalpy of steam. You can get the enthalpy with the help of that. You get the enthalpy of stream 2, and then you can get the dry bulb temperature with the help of the formula for enthalpy. So this is the exercise which is done, the steps in this example, right? So let's look at the calculations. So steam humidification, air humidification using steam. So initial condition was 20 degrees Celsius dry bulb temperature and 8 degrees Celsius wet bulb temperature. If you read it from the table, at this wet bulb temperature, the saturation humidity ratio is 0.006684. So it is 6 grams of water per kilogram of dry air. You can read it from here, right? 8 degrees Celsius, 0.006684. Okay. Now you this is the mass flow rate. Here in this case the mass flow rate is directly given, it's not volume flow rate, and the humidity ratio at state 1 is you can get it with this formula. Right now this formula is well known to you, it has been already used multiple times. This is the formula, so it is to be used for getting the value of W1, because you know the wet bulb temperature and dry bulb temperature. So that's the formula which will be used, right? And with the help of that formula you get the value of W1, which is quite low, 1.82 gram of water per kilogram of dry air. And so you know the W1. Now if you get W2, you can get the rate of rate at which the steam is injected, right? So now when you what is given is that you want 13 degrees Celsius dew point temperature. When you say a particular dew point temperature, actually you are fixing the uh, humidity ratio also. There is a unique combination of dew point temperature and humidity ratio. You can well understand that. When I have drawn this line, okay, a particular dew point temperature 13 degrees Celsius, the humidity ratio is also fixed. You can read it from the psychrometric chart also, right? Or how do you get it from table? Again, very easy, 13 degrees Celsius, whatever is the WS, that's the humidity ratio. So it's 0.009372 or 9.372 grams of water per kilogram of dry air. That should be the humidity ratio at 13 degrees Celsius dew point temperature. So you can directly write it from the table. That's what has been written here. So that's the humidity ratio, final humidity ratio. So how much of steam, or in general it is water, is to be injected in the stream. So it is a mass flow rate of dry air into change of W. So you get 0.015 kilogram per second, right? So it is 15 grams per second. Seems to be a small number, but when you multiply it with 3600, it is 54 kilogram of steam per hour. Of course, as compared to the mass flow rate of air, it would be quite small, right? And now you want to get the dry bulb temperature. For that you get the you will do the enthalpy balance. So you get the enthalpy at state 1. Enthalpy depends upon dry bulb temperature, depends upon W, and with the help of this formula you get the enthalpy at state 1, which is coming out to, because W1 and T1 both are known. So you can get H1, it is 24.735 kilojoule per kilogram of dry air, right? So H1. Now you are injecting steam. So what is the enthalpy of that steam? That is getting added, right? So what is the enthalpy at 110 degrees Celsius, and it is written saturated. So you can get it from the saturation properties of water, and with the help of this table 110, this table is available as of now. It is only up to 69, but it is nothing but the steam table. So from steam tables you can at 110, whatever is the saturation enthalpy, that is Hg. Hg is what you will read, and you can get the enthalpy at that point, right? So it's Hg, saturated vapor enthalpy, which you will read, and that value is to be used. So that should be 2692 kilojoule per kilogram. So that's the enthalpy which is being added. So what with the help of the enthalpy balance, you can get the enthalpy at 0.2. So enthalpy at 0.2 is equal to enthalpy at 0.1 plus mass flow rate of water into upon mass flow rate of dry air. into the enthalpy of the steam which is being injected at 110 degree Celsius saturated condition. So you get the enthalpy at 0.2, which is 45, right? So enthalpy has increased significantly from 24 to 45, right? But if you look at the temperature, now this has been found again with the help of this formula, because you know H2, you know W2, but you don't know T2. So with the help of this formula, you can find out T2, and T2 is found to be 21.1 degree Celsius. What was T1? T1 was 20 degrees Celsius. So temperature has just increased by 1 degree or 1.1 degree Celsius. So temperature rise is not very high. What is mainly rising is humidity ratio and enthalpy. So the steam injection process is will be, that line will be having very high slope, right? Close to 90 degrees. It will not have low slope, as you can see here, and you can also draw it here. This is your initial state, and your final state can be shown because it is 21 degrees Celsius. So you can shift this to 21.1, right? So this is the final point, and then you can draw a line joining these two, which is having very high slope. So that's about the steam injection and the final state that you produced by steam injection. What you could see is mainly the humidity ratio has increased, and because of the higher humidity ratio, the enthalpy also has increased, but the temperature change is quite small when you inject the steam. Right? So this is the this example was meant to develop more understanding and insight into the steam injection process, air humidification using steam injection, adiabatic humidification, not exactly adiabatic humidification, adiabatic steam injection, right? That means from boundaries it is not getting lost, right? It's only the steam which is adding to the enthalpy of air and the moisture of air, right? So in the next lecture we will discuss about the cooling and dehumidification process, which is perhaps the most important air conditioning process.